Hi everybody, Physics Ninja here and welcome to my Geometrical Optics Problems Review session. What we're going to do today is look at 10 problems. I've got 27 questions, looking at all types of problems dealing with refraction, how to use Snell's law. Going to have a lot of problems with lenses. How do you find the image? Is the image a real image or a virtual image? Dealing with magnification, focal distance, and so forth. So this is what you do. You start off by going to the description of this video and click the download link to get the problem set. Work through some of the problems by yourself and come back and watch the rest of the video. It's the best way to learn physics. You got to try out the problems first. All right, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to Physics Ninja. It's the best way to support what I do. All right, let's get started. All right, here's our first problem. It says a monochromatic beam of light passes from medium 1 to medium 2, characterized by refractive indices N1, which is 1.4, and N2 is 1.2. In medium 1, the angle makes an angle theta 1, which is equal to 40 degrees, with the boundary separating medium 1 and medium 2 as shown in the figure over here. Our first question we have is, what is the corresponding angle of the beam of light in medium 2 with respect to the boundary? Alright, so this looks like a Snell's law type of problem. The only kind of trap that you have to be careful of is right now they're giving you the angle here with respect to the boundary. They're not giving you the angle with respect to the normal, which is perpendicular to the boundary. So I'm just going to fill in those details. So if that's 40 degrees, that means this angle is 50 degrees. Now if I'm going to write now Snell's law, I would write N1, I would write sine, and I'm just going to call it alpha 1. Alpha 1 for me is this angle. It's always the angle with respect to the normal. That's how you apply Snell's law. N2 sine of alpha 2. Again, this is going to bend. It goes from a high index of refraction toward a low index of refraction. So guess what? That should bend like this. Should bend away from the normal. And this would be my angle alpha 2, but they are asking me to solve for this angle, theta 2. All right, so we just got to be a little bit careful here. So I'm going to start off by solving for alpha 2. Once I have alpha 2, clearly I can easily find what theta 2 is. So how would we write this? Well, alpha 2 then, and just bring the index and 2 onto the other side. What else? I'm still going to have sine of alpha 1. And here, well, let's give myself a little bit of extra space over here. Move this over. Move this over. And here I should do just an inverse sine function over here. So sine of -1 of this entire term. And now we simply substitute in our values. All right, so N1 is 1.4 over 1.2. And now sine of, this would be 50 degrees here. Okay, when I substitute my numbers into the calculator, I get that alpha 2 here is 63.3 degrees. All right, which means that theta 2 then is going to be 90 minus 63.3 degrees, which is going to it's going to give me 26.7 degrees. All right, so we get C is the correct answer for this one. Next question says, compare the frequency of the light in medium 1 to the frequency of light in medium 2. All right, so one thing to note about the frequency, it does not change when you go from one medium to another. So you have to have this. Now, what is going to change? The speed is not going to be the same, okay? And also the wavelength is not going to be the same. But the frequency will be the same. The frequency is dependent on the source that created this monochromatic beam of light, okay? So for this one here, A is the correct answer. Don't get fooled by that. All right, the last one says, given the index of refraction of material 1 and an incident angle theta 1, it's equal to 40 degrees. In order for the beam of light to undergo total internal reflection at the interface between the two surfaces. All right, so we're interested in total internal reflection. So let's have a look at how we would set that up. Again, for total internal reflection, it means that my angle alpha 2 should at least be equal to 90 degrees right here. So imagine if you substitute that into Snell's law, we would have to get this. N2 sine of 90 degrees equals to N1 sine of alpha 1. All right, and sine of 90 degrees is simply equal to 1. So we get an expression here for what the index of refraction would have to be to undergo total internal reflection. Now what we're going to do is just substitute our values here. We're going to get n1, which is my 1.4. And now again, I'm going to choose the alpha 1. Sine of alpha 1 is still my 50 degrees. If I substitute those numbers, I would need an index of refraction of roughly 1.07. So it would have to be smaller than 1.2, right? It has to be smaller because I want to bend more light. So I want to have a larger difference in the indices of refraction between those two media. All right, so A is probably the best choice for this one. Here's problem 2. Consider the case of light traveling through 3 different materials in layers with indices of refraction N1, N2, and N3 as shown in the figure here. All right, first question says, given the transition between layers 1 and 2 shown in the figure above, what can be concluded about these two materials? All right, we're comparing the index of refraction of the top layer and the second layer. And look what is happening to the light here. It is, again, our normal here is defined up here. That is some angle theta 1. And you can see here that it's bending, right? This beam is not continuing along a straight line. It is bending closer to the normal. So we automatically know by doing this that N2 must be bigger than the index of refraction of medium 1. All right, so that there corresponds to choice C is the correct answer for this one. All right, next question says, if the light is totally reflected between material 2 and 3, which of the following holds? All right, now we're comparing the index of refraction of N3 to what's going on in that top layer. I would start off by writing Snell's law. N1 sine of theta 1 should be equal to N2 sine of theta 2, and that's fine. Now, how about going from the second layer to the third layer? Well, again, I could apply Snell's law to that. N3 sine of theta 3. And now what we want total reflection between 2 and 3. So what we want here is we want to set this angle here, theta 3 equals to 90 degrees. And that's going to give me a relationship. What must be the angles for theta 1 and theta 2? If you substitute 90 degrees for theta 3, that simply simplifies to 1. So you're only left with N3 on the right-hand side of my equation right here. Now, if I'm relating this to what's going on in layer 1, I have this condition, and this would allow me to find really what the critical angle is to have total internal reflection. Now, the angle could be bigger than theta 1, right? This just allows me to find what is that critical angle. But you can certainly have a case where the angle is bigger than theta 1. So really, as long as I can write this, right, that the index N1 multiplied by sine of theta 1 is bigger or equal to N3, I will have total internal reflection. And that there looks like it corresponds to choice A as being the best case. All right, here's problem 3. A light passes from air into a slab of glass at an incident angle of theta equals 25 degrees. The glass here has a thickness H, and at the lower boundary of the glass, part of the ray is reflected and exits the glass slab a distance d away from the location of incidence. All right, so this is kind of what the picture goes. You got that light that refracts when it enters the glass. Part of that ray now gets reflected, and then it will eventually exit over here at some distance d. All right, so they're asking us how to solve for that distance d. Well, I think what I would first do here is I'm first going to find what this refracted angle is here. I'm going to call this theta 2. Once you have that angle, then we can do some trigonometry in order to find what this distance d is. But let's start by applying Snell's law. We have N1 sine of theta 1. The angles are now defined with respect to the normal, so this is looking good. All right, my goal is to find theta 2, so bring N2 onto the other side. I always don't give myself enough space to write this inverse sine function here. So let's try that again. So here I have N1 sine of theta 1 divided by N2. Now we go ahead and substitute in all our values. Sine minus 1. N1 was 1, that's simply air, multiplied by sine of 25 degrees. And now over 1.6, that higher index. Well, one thing we should know is that the angle should be smaller than that 25 degrees. And you go ahead and solve that. I think I get 15.3 degrees as being that angle. All right, now I'm just going to focus on the part of the ray here that is within the slab of glass. So let's draw that slab of glass. I'm going to draw a normal, and let's see what's going on. So we've got this ray that's coming down here, and this is the angle here, theta 2. And now part of it is reflected over here, and we are looking for this distance, which we're defining as d over here. Now we are given other quantities. We are told what this thickness here, we've defined that to be h. And well, if I use some trigonometry, I could probably find what this angle is right here. Not this angle, but this length. I'm going to call this x. And one thing you should see is that my distance d then can simply be found as being 2x. So how would I find, for example, the distance x? I can use some trigonometry. You could see that tangent of this angle theta 2 should be equal to the opposite over the adjacent. That's x over h. If you bring the h to the upstairs, we're going to have one last equation now for d. It's 2 times x, and x is h tangent of theta 2. I'm going to go ahead now and just substitute the values. I am quickly running out of space, so let me go ahead and do that over here. 2 times h is 0.028 meters, and now tangent of, we had 15.3 degrees. Now go ahead and put that in your calculator, and you should get 0.0153 meters. Let's squeeze a 3 in there. All right, and that there looks like it corresponds to choice B as being that correct answer. All right, so what do we have next? The next question says, if the slab is placed in water. So what we're doing here is n over here is going to be 1.3 instead of being 1 like it was in the first case. And the ray of light is incident on the glass surface at the same initial angle. The distance d between where the incident ray enters and the reflected ray exits is going to be less than, larger than, or equal to the value that it was in air. It's certainly not going to be equal, right? Because what's going to happen now? What you're going to end up finding here is that the angle theta 2 is going to be a bigger number. It means you're going to get less amount of bending of the light. You get more bending when there's a large contrast between the indices of refraction of the two materials. But if I have less bending, it means that angle is going to be bigger and the ray is going to hit somewhere over here. And then it's going to reflect at that same angle at which it was incident on that lower surface. So the angle, that distance d that we calculated, we would actually get something that is larger than the value that we would calculate in air. Right? If there was a large amount of bending, right? If that index difference was even bigger than it was in air, then you get a small value of d. All right, so this is kind of a nice conceptual problem for applying Snell's law. Let's go to the next problem. All right, here's problem 4. It says, a light ray is incident from the air into a glass of index of refraction n2, which is equal to 1.5, at an angle theta 1, which is equal to 30 degrees. The angle between the reflected ray and the refracted ray is called theta 2, this large angle over here. So what is the value of theta 2? All right, so for this one, we're just going to break this down into steps. What I'm going to do here, I'm going to apply Snell's law. I'm going to call this alpha 1. I'm going to call this alpha 2. And then I'm just going to use some of those angles in order to calculate what theta 2 is. All right, so the first thing I would do is we're going to use Snell's law. So we're going to have n1 sine of alpha 1 equals to n2 sine of alpha 2. Let's start by solving what is alpha 2. I have the inverse sine. I bring n2 down at the bottom. I get n1 sine of alpha 1 over n2. Now we substitute in all our values. We have inverse sine. n1 is air, so that's 1 over 1.5. And here I'm going to have sine of which angle? This here should be 60 degrees is that alpha 1 angle. So substitute that. You put those numbers in the calculator and we're going to get an alpha 2 value, which is 35.3 degrees. All right, so what does that mean? Well, now I think we can get one step closer. Okay, let's think about this reflected ray. This reflected ray right here has this interior angle here, which has to be 30 degrees. And to that, what I want to do is I want to add this angle down here inside the glass, okay? So what is this angle going to be? Well, guess what? It's going to be 90 minus alpha 2. So at the end, I should be able to write this. the angle theta 2 should be 30 degrees, that incident angle, plus, here I'm just going to write 90 minus alpha 2. Now we just substitute the values, so 30 plus 90 minus 35.3 degrees. And here we get a value of 84.7 degrees. That looks like choice C to me. All right, so this one you just had to be careful, right? How are the angles defined? How are they defined in Snell's law? And just use the fact that, some of those angles, when you add them up, have to be 90 degrees. All right, let's look at the next question. If theta 1 decreases to 25 degrees here instead of 30, how would theta 2 change? All right, well, let's go back and think about it here. So if theta 1 here decreases, what else does that mean? Okay, it means, first of all, that the angle alpha 1 has to increase, because when I add theta 1 to alpha 1, I have to have 90 degrees. All right, so that's the first step. Next thing we can think about, what happens to alpha 2? If I bring alpha 1 and I increase it, guess what I am going to do to alpha 2? I'm also going to increase that angle according to Snell's law right here. Right? If I have a larger angle over here, I'm going to have a larger refracted angle. That's how Snell's law works. So if I increase alpha 2, let's think about what happens to theta 2 now, right? Theta 2 is going to do what? Well, it's nice having this expression, this formula right here, because here we simply have 120 minus alpha 2. And if alpha 2 goes up, it means theta 2 has to get lower. All right, so the correct answer for that one should be choice C. Theta 2 would decrease. All right, that's kind of a nice problem. Let's go to the next one now. Here's problem 5. A monochromatic beam of light passes from medium 1 to medium 2, characterized by refractive indices N1 and N2. So N1 is 1.55 and N2 is 1.35. In medium 1, the beam makes an angle of 39 degrees with the boundary separating the two medium, as shown here in the figure. What is the corresponding angle of the beam theta 2 in medium 2? Notice here that theta 2 is defined here with respect to the boundary. It's not defined with respect to the normal, so that is just something we have to pay attention. So I'm going to call, again, I'm going to just use a different notation here. I'm going to call the angle with respect to the normal alpha 1 and alpha 2. So now I'm able to write down Snell's law. That involves the angle with respect to the normal. Don't make that mistake. Start off by finding what alpha 2 is. It's always the same steps here. N1 sine of alpha 1 over N2. Substitute in our numbers. N1, now I got to be careful. This is 1.55 over 1.35. And multiplied by sine. All right, so what is going to be our angle over here? This should be, that's 39 degrees. This here should be 51 degrees. All right, you put those numbers in the calculator, and I got an alpha 2, which was 63.2 degrees. But again, theta 2 then has to be 90 minus this angle, which ends up corresponding to 26.8 degrees. All right, and that there looks like choice E to me. All right, next question says, compare the speed of light V1 in medium 1 to the speed of light V2 in medium 2. Well, one thing to remember is that the speed of light in any medium with an index of refraction n is given by this value right here. Okay, so what does that mean? Well, if I have a higher index of refraction, I am going to have a lower speed. Right? So since you have N1, which is bigger than N2, it means that V1 is going to be less than V2. And that there looks like it corresponds to choice A. All right, the next question says, given the index of refraction for material 1 and an incident angle 39 degrees, in order for the beam of light to undergo total internal reflection at the interface, what should you do to the index of refraction? Should you make it larger than 1.35, smaller than 1.35, or it's not possible? So what I would do is, what we want for total internal reflection is I don't want this angle theta 2 to be, for example, 26.8 degrees. I want to have more bending of the light. Okay, and I want so much bending that the refracted light ray, that angle ends up being 90 degrees with respect to the normal. Okay, so you want more bending. And how do you get more bending of the light? Is you want to make that index of refraction, the difference between the two, as large as possible. So if I keep this one here at 1.55, what I want to do is I want to make N2 less than 1.35 in order to obtain that. All right. In this case, you can actually even calculate it if you wanted to, right? We can write N1 sine of alpha 1 is equal to N2. And if I want total internal reflection, I want that angle alpha 2 to be 90 degrees. In this case here, you can calculate what the value here is. You simply do 1.55 sine of 51 degrees again. And that gives me a value of 1.2. So you can see what we have to do. We would have to simply lower that index of refraction, right? You want it less than 1.35. You want it equal to 1.2. All right, that's a standard Snell's law problem. Let's go to the next one now. Here's problem 6. A diverging lens has a focal length f1 of -7 centimeters. An object is placed a distance of 24 centimeters to the left of the diverging lens as shown over here. The image formed by the diverging lens is what? Okay, so one thing we have to do is just apply our simple equations. Okay, so what we're going to do is, well, let's just write 1 over f is 1 over O plus 1 over I, or O is the distance of the object to the lens, and I is the distance of the image to the lens. All right, if we're able to solve or say whether I is positive or negative, we're going to be able to answer whether it's virtual or real and upright or inverted. So let's go ahead and think about this. So we have our focal distance, which is, I'll just keep everything in centimeters here, 1 divided by -7. Equals 1 divided by O. What is the distance of the object to the lens? In that case, it's positive 24 centimeters. Plus 1 over I. Now you automatically see that this term here on the left-hand side is negative. Once I bring this term onto the other side just to isolate, I will automatically obtain that I is negative for this problem, right? There is no way for me to solve this and obtain a positive value of I. Okay, so if I is negative, it automatically tells me one thing, okay? If I is negative, it means that this image right here has to be a virtual image. And guess what we know about virtual images? Virtual images are always upright. So that is a straightforward case right here. Choice B is the correct answer. All right, what's the next question? The location of the image formed by the diverging lens. Well, now we actually want to solve what the I value is. So I'm just going to carry out this math a little bit further. All you have to do now is just isolate. So I have 1 over I equals -1 over 7, and then -1 over 24. At the end, just be careful when you do the math. At the end, you're going to get a value I, which is equal to, I get like -5.42, and I've left everything in centimeters here. All right, and that there corresponds to choice C. The last problem says, what is the magnification of the image? Here we simply have to apply our definition for the magnification. It's -I divided by O. So we have minus, that just comes from the definition. Now I is also negative. So we have -5.42. And now divided by O, the distance of the object to the lens. In this case, that was 24 centimeters. All right, we're going to get a positive magnification for this problem, and we get positive 0.23 is the magnification. That there corresponds to choice D. All right, kind of a nice lens problem. Let's go to the next one. All right, here's problem 7. A converging lens made of glass with index of refraction n equals to 1.5 has a focal length of 0.25 meters. The lens is positioned at x equals to 0 as shown. At what position x0 to the left of the lens should an object be placed so that the resulting image has a magnification equals to -2.5? All right, well, I would simply write this down that the magnification then is -2.5, and the definition of the magnification is -I over O. All right, so I have one equation here that links I and O distances together. So I have 2.5 multiplied by O equals to the image. So that's one equation that links them. I have two unknowns over here, O and I, therefore I need another equation. Now they have told me the focal length of this lens, so I can also write this 1 over F equals to 1 over O plus 1 over I. Here's another equation, right? This is a second equation. What I'm going to do here is I'm going to eliminate I in the second equation using the first one. So I have 1 over O plus 1 over 2.5 multiplied by O. All right, and be careful. This is an O, it's not a 0. This is an O. All right, so what we have to do now is simply substitute. O is the only unknown in this second equation right here. So all we have to do is just do a little bit of math. You could factor out a 1 over O term. Okay. Here I'm going to be left with 1 plus 1 divided by 2.5. And this is 1 over F. So at the end, I could have O, which is F multiplied by 1 plus 1 over 2.5. Maybe let's clean up that bracket term a little bit. If I put things on a common denominator here, I should have 3.5 over 2.5. All right, we go ahead now, we substitute. The focal length is 0.25. 3.5 divided by 2.5. At the end, you substitute in all our values. I should get a distance O, which is 0.35 meters. All right, now you look at those choices. There's only one choice that has 0.35, and that is choice A. Here they're looking for a coordinate here, and the 0 is right here at the position of the lens, so everything on this side is negative. Everything on this side here is positive in terms of their coordinates. So, but A is the correct answer for this. All right, so what are we going to find now for I? I would simply have to multiply 2.5 times that value, but we will find that I is a positive value, okay? And if I is a positive value, the definition of that, it means that it is a real images, okay? And real images for us are always inverted, right? Because we're going to have a magnification, which is minus 2.5. That's given in this problem over here. All right, so real and inverted, they always go together for single lens problems. So that's really, really important. All right, the next question says, if the entire apparatus was placed inside an aquarium filled with water, so instead of having air out here, we now have water, which has a higher index of refraction than water. In order to produce the same magnification, so we're still going to have this result over here, what should you do with the object O? Well, think about our expression that we have over here, right? This is really the key to this problem. Looking at this expression, we have F, again, multiplied by a whole bunch of terms here, which are not going to change because we want the same magnification. So what would you do to, where should the object be moved? Should you move it closer to the lens, about the same location, or further from the lens? Well, what is the effect of having everything placed inside water? Is you're increasing that index of refraction, which means that the difference in the index of refraction between the lens and the water is smaller, okay? This means there will actually be less bending of the light. There is going to be less refraction of the light. And that is basically, that has the same effect as having a bigger value of the focal length. Bigger F value, right? And if F is bigger, guess what? Then O should also be bigger, which you could see from that second equation here. That means O is also going to increase. So I have to move it further from the lens. So C is the correct answer for this one. All right, here's problem 8. It says, an object of height h naught equals to 0.22 meters is placed to the left of a converging lens, producing an image, a little bit of a typo here, of height 0.48 meters. And it's 2.8 meters away from the object, okay? And it's to the right of the object. First of all, we see that from this diagram that the image here is definitely inverted, okay? And if it's inverted, that automatically tells you that if there is only one lens, it is a real image, okay? So choice A is the correct answer. The next problem says, what is the focal length of this lens? All right, so this one is not super clear how to do, but let's go ahead and write down what we know. I'm going to call this distance here, I call that O, and I am going to call that distance here I. I is the distance from the lens to the image, O is the distance from the object to the lens. We're going to have to solve for F, so let's write down an equation for this. We have 1 over O plus 1 over I. Okay, so we have one equation and we have two unknowns. So guess what? I need to figure out what O and I is. But now I can use the fact that I know this height of the object in the image, because that is related to that magnification. And the magnification is minus I over O, or you can also write it as minus, right, HI divided by H0. All right, so what you're going to find is that the magnification here has to be a negative value, right? And if you substitute hi and ho over here, you're going to see, in fact, that it is a negative value. Okay, so let's go ahead and substitute our numbers here. So what do we get? We get minus 0.48 and divided by 0.22. Now that gives us a relationship here between I and O again. Okay, so if I actually just get a number for this, I am going to get a number that is equal to 2.18. So my equation now is I over O equals to 2.18. So now we have a second equation. What I could do now is I can combine both of those equations and in order to get to the focal length. The other information, I'm also given this value here. L is equal to 2.8 meters. So what is L with relation to this figure over here? I have that L is equal to O plus that distance I. Right? So now we can really kind of just plug and chug and get actually values of O and I based on only these two equations right here. Once you have O and I, you go back and substitute into my first equation to find the focal length. All right, so let me start off by combining both of those. So what you're going to get here is L, which is equal to O plus, and instead of substituting I here, I'm going to write I as 2.18 multiplied by O. You factor out the O, you get 3.18 multiplied by O, and my L value was 2.8 meters. All right, so we can go ahead and substitute. Okay, so we should get O is equal to 2.8 over 3.18. That gives me a value of 0.88. That should be in meters. And what else? Now the I value I can get, because I is simply 2.18 multiplied by 0.88. That gives me a value of 1.92 meters. All right, now we go ahead and we substitute everything back into the equation. So 1 over F equals to 1 over 0.88 plus 1 over 1.92. That allows you to solve for that focal distance, and I got a value of 0.603 meters when I substituted the values in the calculator. All right, so there's quite a lot of steps to this problem, but again, it's just a matter of writing knowns and unknowns and our relationships, right? We have an equation that relates the focal length to the object in the image. We're also told something about the magnification, and we were told this distance over here between the object and the image. So by combining all of these three, I was able to get to the focal distance. So A is the correct choice for this one. Here's the rest of problem 8. It says a block of glass of width 3.4 meters is placed just to the right of the lens. A ray is incident on the block at an angle theta I equals to 40 degrees and refracted such that it makes an angle of 28 degrees inside the glass. How does inserting the block of glass affect the location of the image? All right, well, first of all, what would this glass do, right? It seems like it has the effect of producing less bending, right? The lens bends it quite a bit, that ray, and now this here kind of reduces the effect of the bending just due to the refraction inside the glass, right? So if I think about it, overall, it basically makes it look like this lens has a longer focal distance, okay? That's basically what it does. So it's like having a lens with a longer focal distance. So what would that do? That means you're going to have the effect of bending less light. So what it should do is it should move the image further from the object, okay? So I think A is probably the best choice for this. The next question says, what is the index N glass based on all this information? Well, we are told this angle, 40 degrees. We're also told the angle inside the glass. So this is a straightforward application of Snell's law. We also notice from the figure that the angles are defined with respect to the normal over here. So therefore, we are good to go. So I can write N1 sine of theta 1 equals to N2 sine of theta 2. My goal is to solve for N2 in this case, right? So N2 is equal to N1 sine theta 1 over sine of theta 2. Our values here, N1 is just the value in error, so that's just 1. What do we have? Sine of 40 degrees, and here we're going to have sine of 28 degrees. put those numbers in your calculator. You should get that the index of glass is approximately 1.37. Okay, so B is the correct answer for this one. All right, let's go to the next problem now. Problem 9 says an object is placed to the left of a diverging lens as shown below. The point labeled F is the focal point for the lens. Which of the three rays shown is not correct? Well, let's look at ray A. Ray A is a ray that runs parallel to that axis down the middle over here. And the rule is it's going to bend away from that, and it appears as though it is coming from the focal point. All right, so that ray A is okay. Ray C, on the other hand, a ray that goes through the focal point gets refracted in such a way that it should be parallel to the axis. So that one is also okay. The one that is wrong is ray B, because if I draw the focal point on this side of the lens over here, a ray that appears as though it's going through the focal point should be refracted parallel to the axis. And you can see here that this one here is not parallel. So that one would be incorrect. Okay, so I would go with B as being the correct answer. Now, they're asking you, you haven't been given a lot of information other than it's a diverging lens. They're asking you, the image is upright or is it inverted? All right, so one thing to think about here is how do we solve this? We would solve something like this, 1 over O plus 1 over I. And we're looking for information about the image. But whenever you have a diverging lens, the convention is that F should be a negative value if we're going to use this equation here. Okay, so that means that we're going to have this term as negative. Now, my object distance, for me, I always define that to be a positive value, right? O is always positive. But when I bring that term onto the other side, because I want to solve for what the image is, notice when I bring it to the other side, it will become a negative value. So I here is always going to be negative for a diverging lens. If I is negative, that automatically should tell you something, right? That automatically tells you that the image here is going to be upright, and the image is going to be to the left, right? To the left of this lens, on the same side as the object, okay? So this is also called a virtual image. All right, good problem. Let's go to the last one now. All right, here's problem 10. An object 5 centimeters high is located x1 centimeters, 75 centimeters from a converging lens with a focal length f1, which is equal to 50 centimeters. A second converging lens of focal length f2 is located 200 centimeters from the first lens. All right, an image of the object is to be formed on a screen 175 centimeters from the second lens. All right, so we're given a bunch of distances here and the focal length. We're not given the focal length of that second lens, but we are told where that final image is located. What must the focal length f2 of the second lens be so that the final image appears on the screen? All right, so for this one, I would just start by setting up what we do know. I would start off by the first lens. We do know its focal point, so I can write down my equation, and maybe I could find where is the image I1 for this problem. All right, so all we have to do now is just substitute our values. Here we know that the focal length is 50 centimeters. That's given in the problem. What else? X1 is 75 centimeters away. All right, and now we simply have one equation and one unknown for this problem. All right, so we bring that onto the other side. You solve for I1, and I should get I1, which is equal to 150 centimeters. All right, so 150 centimeters is going to be, say, right around here, right? Because this whole distance here is 200 centimeters. All right, what else? Well, once I have that, now this image becomes the object of the second lens. So now I have to write down a second expression. 1 over f2 equals to 1 over o2 plus 1 over I2. So this image becomes, guess what? The object 2, like this. So now if I substitute everything inside my second equation here, I could eventually solve for the focal length. So what is this distance over here, I2? Well, they are telling me here that an image is formed on the screen, and they told me that this is 175 centimeters. So that is the distance I2 right here. So this is all we have. We have 1 over 150 plus 1 divided by 175. Okay, and now we simply solve for f2. That's 1 over f2. All right, well, you put the numbers in the calculator, and you should get f2, which should be equal to 38.89 centimeters. And that there looks like it corresponds to choice D. All right, they say the final image formed on the screen compared to the original image is what? Well, first of all, I can get rid of choice A. There definitely is an image. They told me that in the problem set. All right, so we have real images or virtual, and then they have upright and inverted. All right, so one thing we got to be careful here is if there's two lenses, you could have a real image that is upright. Okay, so we have to be a little bit careful, and we could have a virtual image that is also upright. Okay, so or inverted rather. So you just got to be a little bit careful when there's two lenses. Every combination is actually possible. So what I would do for this one is I would first look at this magnification, right? What is the total magnification? Well, I'm going to get minus, well, the total magnification is simply the product of the magnification from the first lens multiplied by the magnification from the second lens. So I get minus I1 over O1, and then what? Multiplied by minus I2 over O2. Okay, so one thing to notice here is that I1 and O2 are the exact same values, right? So those negative signs also cancel out, and I have here I2 and O2 are the same. So all we're left with here is this ratio of I2 over O1. I2 was 175, and O1 was 75. Okay, so my total magnification for this problem right here, well, the only thing I really need to see is that it's going to be a positive value right here because those negative signs canceled out. Okay, if it's a positive value, it means that the image is going to be upright. So I would get rid of anything that says inverted right away. Okay, and since there is light here that's being projected on the screen, what you're going to have here is you're going to have a real image. Okay. Going to be a real image because you're able to project it on the screen. All right, so B is the correct answer. All right, folks, that concludes this problem set. Hopefully you enjoyed it, and we'll see you next time.